A discussion at the end of the last talk in the afternoon. So we shorten a little the poster session, and we have the discussion there. So about shearing bending during dynamic yielding, Susan.
Thank you. So thank you for the introduction. I'd like to give an overview talk of some work that we've been doing in my group in Durham over the last 5 to 10 years. Concerning one basic idea, really, that being the notion that when you start with a material in a solid elastic-like state, and then it undergoes a transition to a fluidized flowing state via a process of dynamic yielding, then you should quite generically, whatever the material, whether we're talking about a polymer melt or a yield stress fluid, as we're thinking about more in this meeting, that you should quite generically see shear bands form during that process of dynamic yielding, even if they then heal away to give a homogeneous final flowing state. So, because it's more the focus of this meeting, I'm going to focus this talk on yield stress materials, and depending on which part of the literature you've grown up in, one might variably use the rubric yield stress materials, soft glassy materials, or elastoplastic materials. I'm not going to distinguish between those classes today, but they all have the basic feature of having a static yield stress in the flow curve in the limit of a zero strain rate. But I would like to emphasize again, actually, that what I'm about to say today isn't only restricted to that class of materials, but also crops up in ergodic materials like polymer melts that don't have a static yield stress. In this second part, I'm then going to basically communicate the take-home message of the talk, which I'm then going to exemplify later on. So the take-home message really is quite simple, and that's even in the large subclass of materials that don't support shear bands in their ultimate steady, fluidized, flowing state, that nonetheless, when you start out in an initially solid-like state, and the material transitions to that final fluidized state via a process of dynamic yielding, that one should quite generically see shear bands form. So that's the take-home message, and the rest of the talk will be exemplifying that message in the context of a particular model. And I've chosen the particular model, that being the soft glassy rheology model, which I think I've chosen because it's probably the most familiar one to this audience. But again, I'd like to emphasize that these results aren't specific to this model, but crop up in many other models of yield stress fluids, but also in ergodic materials like polymer melts as well. I'll then separately talk about the two most common yielding transitions. The first, where you impose a fixed strain rate and track the stress as a function of time, and second, where you impose a constant shear stress and track the strain rate as a function of time, and demonstrate the formation of shear bands in both of those. Now, in each of those cases, there's a single yielding transition where you start from a solid-like state and go to a liquid-like state just once. On the other hand, one can also think of flows that have a sustained time dependence, such as a large amplitude oscillation, where you're constantly oscillating the material. And what I'll show there is that you can have sustained yielding within each cycle, and associated with that, so you can have yielding in each half cycle, and associated with that, shear banding in each half cycle. Okay, so the kinds of materials I'm focusing on today are so-called yield stress materials. So for people in the soft matter physics community, you might be thinking of dense emulsions, foams, colloidal suspensions, so-called surfactant onion phases, or suspensions of bead-like gel particles. In harder materials, one might think of polymeric or metallic glasses, but then one might also think more generally of collections of cells in biological tissue, and for many people in this audience, I know geophysical problems such as sea ice flows, earthquakes, and so on. And the basic notion here is that these materials share some features in common. So if we focus for definiteness here on an emulsion with a high packing fraction of bubbles here, we see that it's structurally disordered packing. And because the bubbles are tightly packed in together, they're stuck in metastable states and struggle to rearrange relative to each other. So they're in metastable configurations, and they can't properly explore phase space. So in the language of statistical mechanics, the ergodicity is broken. And the most obvious feature that these materials have in their rheology is that in the steady state flow curve, so that's the relationship between the shear stress, the force per unit area at the wall, and the shear rate, that's the plate speed normalized by the gap size. So in a steady flowing state where nothing's changing as a function of time, then the most striking feature is that at a high packing fraction of the droplets, then as one extrapolates the shear rate to zero, one doesn't see the stress go to zero as one would in water, for example, but it extrapolates to a non-zero constant, and that's called the static yield stress. And so the picture that one then has is that material is in a solid-like state below the yield stress, but in a fluidized flowing state above the yield stress, where we have a flow state that looks like this. Now, on the next slide, I just want to present an aside, which I'm then going to dispense with for the rest of the talk, but I do think it's important to go through it and then dispense with it. That being that there is a subset of these materials in which the relationship between the shear stress and the shear rate, computed within the assumption that the flow is homogeneous, has a region of negative slope here. And that's an unstable state of affairs. It's trying to tell us that a faster flowing system has less stress. So the idea is that if you start in any calculation with a state of homogeneous flow in this region, and then perform a linear stability analysis in which you add to it small amplitude, initially heterogeneous perturbations, you will find that they are predicted to grow, taking the system away from the homogeneous flow state into a shear banded state. And so the ultimate steady banded state for this subset of materials is one in which there's a coexistence of two shear bands, a stuck band and a flowing band. And this has been seen experimentally, by no means an exhaustive list, and thought of by theorists as well, including myself, and I know also people in this audience. What I want to do now is dispense with this notion. So for the purposes of what I'm talking about today, I'm not considering materials at all that can support shear bands in a steady flowing state. I'm only considering materials that have a monotonically increasing stress as a function of strain rate. Okay, so having focused in on that class of materials that in the ultimate steady fluidized state flow in a homogeneous way, I now want to talk about the process of dynamic yielding. So far we've just introduced this notion of a flow curve with a solid region here where the material can support a stress without flowing, and a fluidized flowing state here in which the flow state is homogeneous in the ultimate steady flowing state. And I'd just like to take the opportunity to define here the axes that I'll use for the rest of the talk. So the flow gradient direction will always be denoted y, and the main flow direction will be denoted x. And as I've said, this steady flowing state here on this fluidized branch is homogeneous by definition, because I've purposefully excluded those materials that show shear banding in a steady flowing state. But of course, to establish this flow state, starting out with a material that's initially undisturbed and well relaxed and in a solid-like state, one has to go through a yielding transition. So one starts out with a solid-like material and then goes through a transition to a fluidized flowing state. And the basic idea that I'd like to communicate, which I think actually has cropped up now quite widely in several of the kinds of simulations that get done by people in this part of the research community, but something that I think has really until very recently been completely underappreciated by the sort of more conventional rheology community, for example, is that to get from an initially solid-like elastic state into a finally flowing fluidized state, one goes through a yielding transition. So the most common way one does that is to start with an initially rested material, and then you suddenly jump the shear rate to some constant value, and you then hold that fixed for all subsequent time. So that's called a shear startup experiment. And you then track the stress as a function of the time since the inception of the flow, or equivalently of the accumulating strain. Now, in the limit of long times, that has to settle to the steady state flow curve value. At short times, however, the stress increases linearly with time, and so with accumulating strain. So that's elastic solid-like behavior. And then there's typically an overshoot, and then as one comes off the overshoot, there's a region of decreasing stress as a function of time. Now, what we did in this paper here was just in a very, very highly generalized continuum model, which could apply to both yield stress materials and to ergodic materials such as polymer melts, was to perform a calculation in which what we first did was compute the startup transient within the assumption, with it by imposing by theoretical fiat that the flow remains homogeneous, shear, and we computed a startup transient that looks like that. And then we did a linear stability analysis showing that if you add to that homogeneous time-evolving state small amplitude perturbations that are the precursors of shear bands, then quite generically those are predicted to grow in this region of stress drop here and grow to then lead to the formation of shear bands. So note in this picture that I'm presenting here, the direction of causality is that even in the homogeneous model, there's a stress drop, and that stress drop causes the shear bands, rather than, I think, the interpretation that's often applied to simulations, which is that shear bands form and they cause the stress drop. So that's actually an important mental switch here, I think, for how one might interpret simulation results. And then because I've restricted to the subclass of materials that flow homogeneously in steady state, those shear bands then heal away. Now, there's another common protocol that's done instead of shear startup commonly, and that's to take a well-rested material, and instead of jumping the strain rate, you jump the stress to some constant value and then hold it fixed. and then you examine the way the material creeps. So you've applied a constant load, and you're asking how the strain evolves, how much the material creeps by. The creep curve is the strain as a function of time. Here I'm showing the time differentiated version, so the differentiated creep curve on a log-log axis. Now, in the limit of long times, that has to get to the value on the ultimate flow curve. Typically, there's a region of sublinear creep here. This is sometimes called Andrade creep in the metals literature, where on this log-log plot, the strain is going down as a sublinear power in time, the strain rate, so the strain would go up as a sublinear power. The strain rate then undershoots, and that corresponds to the viscosity overshooting, and then one wakes up and starts to flow. So there's a yielding transition here. And what we did again in this paper here was show in a very generic class of models that if you first of all compute the creep curve, the differential of, imposing by theoretical fiat that the shear has to remain homogeneous, and then separately do a linear stability calculation where to that homogeneous time evolving state you add small amplitude perturbations that are the precursor of a shear banded state, then you can show on quite generic grounds that those perturbations must grow as a function of time in this region here to lead to a shear banded state that is, however, only transient because the, oh, sorry, that's the wrong diagram there. Right, so that should be homogeneous flow there. Sorry, I pasted the wrong diagram. So it gives way finally to homogeneous flow in the steady flowing state. Okay, so now both of those protocols I've discussed there, there's just a single yielding transition. You're starting out with a solid-like material. You're then forcing it into a fluidized state, either by the imposition of a constant shear rate or a constant shear stress. The material evolves as a function of time to a new steady flowing state. It yields as it does so, and it shows shear banding on the way. One may, however, impose from the outside a flow that has a perpetual time dependence by oscillating the shear, for example. You can either impose a shear of some amplitude, a shear strain of some amplitude, or a shear stress of some amplitude as a function of time. So this is a very, very hot topic in the rheology literature at the moment. It's known as large amplitude oscillatory shear, and it's used to fingerprint the rheological behavior of materials. And depending which you've imposed, you then measure the other one as a function of time, and then removing time as the parameter, you parametrically plot the stress as a function of strain on this so-called Lissajous, or sometimes called Lissajous-Bowditch curve, shown here in this elastic representation. And the basic take-home for what I'm about to show you later on is that in each half cycle now, you have a regime in which the material is behaving elastically, where the stress increases linearly with the strain, and the system isn't then shear banded, as seen by this colour scale here. And then there's a yielding transition to where the stress then doesn't change very quickly with strain. And as one approaches that yielding transition and goes beyond it, you see the formation of shear bands as shown by the red colour scale here. So the colour scale is characterising the degree of banding in the system. So in each half cycle here, you have a yielding transition and the formation of shear bands. And then it goes homogeneous, yields again, shear bands, homogeneous. All right, so that's the basic take-home message. And what I'm going to do for the rest of the talk is exemplify that in one particular model. So the take-home message is that for the large subset of materials for which the steady flowing state, the shear stress as a function of shear rate is monotone increasing, so the eventual steady flowing state on the fluidized branch must be homogeneous. Nonetheless, as you force the system to yield from a solid-like to a flowing state, either by a shear startup or by a step stress, then the system has to transiently form shear bands, which nonetheless then heal away to give finally homogeneous flow. And if you force the system to repeatedly yield, for example, in a large amplitude oscillatory experiment, then you repeatedly see shear banding in each half cycle. Okay, so the rest of the talk, as I've said, will be giving evidence for this in one particular model. That's the soft glassy rheology model, as applied to dense emulsions, foams, gel bead suspensions, and so on. However, as I said, I would like to emphasize, and I've chosen that model because I think it's the most familiar to this audience, but we've demonstrated all the same phenomena in a very simple continuum model of soft glassy materials, but actually also a continuum model of entangled polymer melts, worm-like micelles, highly entangled polymer solutions based on the tube model that dates back, of course, to Dijen, Doy and Edwards. And now, those materials even lack a static yield stress. So as you extrapolate in the flow curve, the strain rate down to zero, the stress goes to zero, so there's no static yield stress. But nonetheless, when you start at the shear, you see strong stress overshoots. In creep, you see creep and then yielding. And in models of that behavior, we've also shown all the same shear banding associated with dynamic yielding. And motivated by the generic appearance across broad classes of models, that motivated this paper here, where we derived highly generic, in the form of a sort of highly generic criterion based on the shape of the startup transient, the overshoot, or the undershoot in the creep curve. And also, just to convince people that there's something in what I'm saying, moving away from the world of continuum modelling, and this is by no means exhaustive, apologies to anyone if I've left off, but shear banding has been seen experimentally and also in molecular simulations, both in shear startup and in step stress, in these papers here. All right, so now let's move on to present the model in which I'll exemplify this behaviour for the rest of the talk. So this is the so-called soft glassy rheology model, and it's aimed at, for example, a dense emulsion. It notionally divides any dense emulsion into many mesoscopic regions, each of which, say, has a few or 10 or 20 or say foam bubbles. So small compared to the sample as a whole, but large enough to be able to define a local strain and stress. And the fact that the bubbles are stuck relative to each other in the absence of flow is captured by representing these particles as residing in traps, so they have zero local strain in the bottom of a trap. Now, when you globally apply shear, the local strain follows the global one in the absence of any plastic yielding events, but once you get to the top of a trap, there's then a plastic yielding event in which you then relax your strain and stress and jump into another trap. These plastic events can also be activated by something that looks like a temperature, which may be a true temperature in some materials, but may also instead model in a sort of mean field way this idea that when an event occurs somewhere, there's an Eshelby propagation which then causes another event somewhere else. Although I should say it's a failing of the model that has never been made properly self-consistent. If one then assumes that this landscape of trap depths has an exponential tail characterized by a parameter x subscript g, this model then shows a glass transition with a glass phase for noise temperatures x less than 1 in our chosen units. The macroscopic stress is then the average over all the particle ones, and the model shows a yield stress in the glass phase. Now, in the form as I've described it, that can only do homogeneous flows, but we extended it to allow for heterogeneous flows and shear banding in this paper here. Okay, so the model then captures the most fundamental feature of yield stress fluids, that is, as I've said, a yield stress. So this is the steady state flow curves here for above x is 2, between 1 and 2, and in the glass phase x less than 1, where there's a yield stress, so the stress extrapolates to a non-zero value at low strain rates. And this is monotone increasing, so the ultimate steady flowing state has to be homogeneous. Now let's go on to look at dynamic yielding in this model. And I'm going to consider the protocols of shear startup and step stress in turn and separately. So first of all, shear startup. Now, first of all, I'm going to show some experiments and then show the results of the model. I've chosen here the experiments by the Leon group on carbopol gel. This is the steady state flow curve of shear stress as a function of shear rate, which has its static yield stress. Notice that 0 is down here. And then what the authors did was now take an initially rested and relaxed sample and jump the shear rate to some value 0.1, I think it was, in the experiments, and watch the stress evolve as a function of time. So it eventually has to fall onto the steady state flow curve, and the flow there is homogeneous. Initially, the stress increases elastically, but on a timescale so fast it's not seen on this axis. And then there's an overshoot and a very, very slow progression to the ultimate steady homogeneous state. Now, shown here are the snapshots of the velocity profile as a function of position across the gap from the moving plate to the static one. Homogeneous flow is where this line just has a constant slope, because this is the velocity as a function of position, so the differential is the shear rate as a function of position. So this is homogeneous eventually in the steady flowing state, consistent with the monotonic flow curve. But as you come off the overshoot, you see the formation of bands, a high shear band coexisting with a low shear band. So now let's see if the SGR model captures this. So shown here on the left-hand side are the results. So focus first of all just on the dotted curves. So this is in an experiment where you prepare the model at some time 0. You then leave it undisturbed for a time tw, and you then impose shear of some constant rate and look how the stress evolves as a function of the accumulating strain, or equivalently the time since the inception of the flow. And you see it eventually settles to a value on the flow curve. Initially it behaves elastically, and there's an overshoot which depends strongly on the age of the sample. So older samples have a much stronger overshoot. Now this is computed within the homogeneous model. We then run the model in the form that allows for the formation of heterogeneous shear banded states. and that's the solid curves. And you see that these align with the homogeneous model initially. That's because the flow remains homogeneous, even in the model that could allow heterogeneity. But as soon as you go near this overshoot, there's a very precipitous stress drop that eventually, not actually on this scale of strains, reaches the steady state flow curve value. And concomitantly with that, you see the formation of shear bands. So this is shear rate as a function of position across the gap at several strains that are actually way off the scale here. And you see a very pronounced shear band initially, then gradually irons out to something that starts to look homogeneous at long times. And I've explored the way the very long life of the bands on the next slide. So these are snapshots at strains of 4, 100, 250 and 800 after the flow started. And you see here a very pronounced shear band that then gradually coarsens away to leave a state of just homogeneous but nonetheless flickering avalanches in the ultimate homogeneous steady flowing state. Homogeneous in the statistical sense, even though there are still flickering avalanches. So I've characterized here this strain required to reach an eventual homogeneous flowing state. So in other words, the strain lifetime of the bands as a function of the imposed strain rate, which I've chosen to express in units of the inverse age of the sample before shear. And this increases as a power to the quarter in these numerics. Now, this is actually telling us something quite important here, because this says if you choose a gamma dot TW value as large as you want, you can get the strains to persist as long as you want. Now, how do you engineer a large gamma dot waiting time value? Well, you can do that even with a shear rate that's as small as you want, so long as you take an old enough sample to start with. So in other words, you can have a very, very slow flow state in which the bands persist for many strain units, but because the flow rate is very small, that really is an inordinately long time for which these bands will persist. So although this is a technically transient behavior, it nonetheless is one that could persist for longer than the duration of any feasible experiment. Okay, so that's a shear startup experiment. I'm now going to talk about a step stress experiment. So you prepare the sample, leave it, although we're not considering the age here. You then impose a stress of some value, and this is the time differentiated creep curve. So we see a regime of sublinear creep, yielding, and then eventual flow, which is homogeneous. Now, there's all kinds of complicated stuff happens as the sample yields, including total wall slip. And this is actually quite widespread across the experiments, and something that theory has done a very poor job of calculating so far. I mean, the vast majority of theoretical work simply assumes no slip at the wall. That's a really serious failing of where theory is at the moment compared to experiments. Nonetheless, as well as wall slip, one does see a regime of bulk shear banding, as you can see at these two times here. So there's a high shear band coexisting with a low shear band, and then eventually goes to homogeneous flow. So we explored this here in the SGR model as suited to capturing shear banding. So this is all for one waiting time, but these are differentiated creep curves for different values of imposed stress above the yield stress. So in each one you see a regime initially of sublinear creep, and then yielding, and then final steady flow. And this panel here, corresponding to each of these curves above, is a measure of the degree to which the flow inside the sample is shear banded. You see it small initially and finally, so homogeneous flow initially and finally, but as the sample yields and starts to flow, the degree of shear banding becomes large, and you indeed see at these two places here strongly banded states. 3 minutes, okay, thank you. Okay, so I was going to talk about flows with a sustained time dependence. I don't have time to, but I do just want to get across the message that one sees a very strong shear banding effect in each half cycle due to repeated yielding in each half cycle. And in fact, one particularly interesting thing is that that even appears to persist. So this is the amplitude of the imposed oscillation, and this is the frequency. My intuition was, and this is the degree of shear banding in any single Laos experiment with a given amplitude and a given frequency. My intuition was that the degree of shear banding, as shown by the red scale here, would decrease at any fixed imposed amplitude as you took the frequency to be smaller and smaller, because then one would expect to be just slowly sweeping up the steady state flow curve, which is shown as dotted in here. There's no evidence for that, and indeed there shouldn't be, I only realised later, because my intuition stemmed from thinking about ergodic polymeric materials where there's a finite relaxation time, which you can always take the frequency to be low compared to. In these aging glassy systems, there is no fixed relaxation timescale. The relaxation timescale is actually then somehow set by the frequency, so you can never reach a state where you're shearing slowly compared to the aging time. And so that means that shear bands persist in this oscillatory flow even in the limit of effectively zero frequency. So as a sort of wilder suggestion stemming from this very particular piece of work, it may be that aging glasses quite generically show shear bands even in flows with an arbitrarily slow time variation. So to summarise then, shear banding is predicted to arise in dynamic yielding in yield stress materials, but also in ergodic fluids such as entangled polymers and worm-like micelles, and indeed quite generically. We've shown that in Shear Startup, in the creep experiment, in large amplitude oscillatory shear, and in other protocols which I've not shown here, but you can read about them, for example, in this paper. So open questions then. So I think it would be interesting to look in more detail at the link between these bulk shear bands, as I've talked about here, and avalanches in these elastoplastic models. I think yielding in the bulk versus at the wall is a very underexplored area. Similarly, the community is mostly focused on shear rather than extension. There's a strain commonly localizes in extension too, and I think it would be good to look at that. An obvious question, of course, is can we prevent strain localization during yielding, or are we just stuck with it? And I think as someone who works perhaps more as much in the rheology community as statistical physics, there really is a pressing need for better continuum models of yield stress fluids to enable a pathway to do computational fluid dynamics of yield stress fluids. And just finally, we're starting to explore this idea of wall slip, and just a quick advert for a simulation method that we've developed that really does properly the solid and fluid mechanics of elastic particles, properly resolving all the Newtonian Stokes flow in the films in between, and considering walls of any prescribed bumpiness that are hard, and properly resolving the mechanics of the wall and the bubbles next to it. And you see all kinds of bulk banding and wall slip, and we're in a position to characterize how much slip you get according to how bumpy the walls are. But I've run out of time, so here are some papers on the story in polymers for anyone who wants to read about them. And I'd like to thank my co-workers, Hugh Barlow, Thibaut Divu, Sebastian Manville, Robin Moorcroft, Ranga Radhakrishnan and Gerhard Young. And also to thank the UK's EPSRC and the European Research Council for funding. Thanks again to the organisers, and thank you for your attention. So we're in the process of characterising that at the moment. That's in progress. Yeah. Lisa Manning did some very nice work on that in the STZ model, whichever you want to call it. So there was a very nice paper in PRE looking at that effect in that model, but I don't recall how it grew. But she characterised it very well. Yeah. We don't know. Yeah, I don't know. That's work in progress. And actually, my student there just focused on one particular value of the noise temperature. He now has data for the other values of noise temperature. And that seems relatively robust. But when we went down very low, but the numerics get hard there, it seemed to vary. So that's open as far as I'm concerned at the moment. Yeah. Yeah. Ah, okay, right. And also temperature, was this the one with Chowdhury and Horbach, or was that a different study? Or no? Okay. Ah, okay, right, yeah, okay, yeah. Right. Okay. Okay. Right, okay. Was that in the JOR in 20, which paper was it? The 2070, okay, right, yeah, okay, I'll have another look at that, thank you. Hi.
So I guess you just partially answered because you said you have your students looking at different noise temperatures.
Yeah.
But
right.
in general, are you like very deep in the glass? Like what's the...
Well, so the one I showed there was 0.3 and the glass transition happens at 1. So, yeah.
And do you
That's
expect everything to be qualitatively the same up to XG, or...?
I wouldn't like to guess. He looked at 0.7 and it seemed to be 0.25. The exponent seemed to still be 0.25 at x is 0.7. But we haven't gone higher than that yet. Yeah.
So, both in the STC model, I guess you're referring to the 2010-2011 work at least.
I think so, yes. I don't recall the exact year. Yeah, it was in PRE. Yeah.
And I guess also here, the space, sort of the spatial description is introduced by adding just a diffusion term. I mean, that was true in
right.
work.
Yes.
I guess
yeah.
also here, right? Is that real? I mean, is that sort of meaningful in all situations? And is there anything else that can be?
Yes. Okay, so in truly continuum models like a fluidity model or in the tube models, it's true that we do put a diffusive term in. Actually, though, it turns out that the criteria for the formation of bands is very highly independent of that diffusive term. So you have a dispersion relation as a function of wave vector, and that's generally a plateau up until you get to wave vectors of order the inverse diffusion length scale. And so bands form on a macroscopic scale. You really just need the diffusion term to save you from having very tight interfaces on very short length scales. The way space was put in the SGR model here, so what we did, we have a one-dimensional version and also a two-dimensional version. In both of those, we have stress properties. So as you know, the SGR model has these plastic relaxation events, as in an elastoplastic model. And the original homogeneous version of the model didn't allow for coupling between those plastic events. In the 1D model, we do that by having effectively integrating the Eshelby propagator over 1D. And in the 2D, we have an Eshelby propagator as in the elastoplastic models. Yeah. So.
The oscillatory work you showed, where does this stress overshoot come from? I mean, because in simulations, one do not see this in the oscillatory protocols. So, because
Sorry, in simulations, one doesn't see the...
molecular dynamic simulations,
You don't see an overshoot, you say?
Yeah.
Okay. So that varies, actually. I mean, some experiments see it and some don't, I think.
No,
Yeah.
you do see it.
Okay.
after once you reach a steady state, keep
Yeah, I mean, there's no smooth maximum.
Mm.
We do see a drop,
Okay.
but we do see hardly any drop.
Last question.
yes, so we showed simulations on your plane that where you have this shear banding, you can have 20 different shear bands.
Ah,
So when you serve the SGR on the line,
yes.
and you take the, I don't know what fixed is the system size, but you take a very large system to
Mm.
see 20 different
Right, so what we did... Yeah, okay.
The related question is,
Yes.
in the experiment you showed the sample is millimeter size, so the T-board.
Mm, right, yes, yeah. Okay.
You only see one band, so what's the generic scenario?
Yeah, right. So I think that's something that's seen a bit differently in the rheology community, maybe as compared to more the statistical physics community. So the rheology community, I think, generally are motivated by how experiments are done actually in rheometers. And okay, this sketch that we draw of planar shear is, you know, that's a theorist's cartoon, and the rheometer will always in practice have some curvature to it, which means that there's some heterogeneity forced by the rheometer because the stress is larger near the inner cylinder than the outer cylinder. The same is also true in cone and plate, but a bit more complicated. And so the way that one then seeds the bands in the first place, you can either impose that there's a slightly heterogeneous stress field across, but what we actually do, well, we've explored several different ways of putting in noise to the system, but in that particular simulation there, I actually assumed a slightly heterogeneous age at the start of the, so it's slightly older in the middle than at the outside. You can also put in, so if you put in truly spatially random noise in this thing, so there being no sort of systematic heterogeneity across the cell, then generally we see multiple bands form, yes. And that occurs even in the models of polymers as well. So I think there are open questions there about what regime it's relevant that one just sees one band and what regime it's relevant that one sees many. Yes, certainly.